Every second, space around you is getting emptier. Measurements confirm it. 2 billion light-years of near-nothingness may already surround us, and we have been measuring the universe as if we stood on flat ground, when we might be sitting at the bottom of an enormous cosmic hole. We are going to visit the voids inside voids, the cold scars on the oldest light in existence, and the gravitational mystery pulling our entire galactic neighborhood towards something we cannot yet see. If you enjoy what we cover here, subscribing means you will not miss what comes next. Brace yourself. We begin. Look up at the night sky, and everything seems packed. Stars everywhere, light in every direction. But zoom out far enough, and the universe reveals a completely different face. At the largest scales, matter in the universe arranges itself like a cosmic spiderweb. Galaxies cluster together along thin threads and flat sheets. Where those threads intersect, you get enormous knots of thousands of galaxies piled together. And between those threads, almost nothing. Vast, dark, nearly empty bubbles called cosmic voids. These are the dominant feature of the universe. Emptiness wins. By volume, voids make up somewhere around 80% of all space. 80%. That means the universe is, structurally speaking, mostly hollow. The galaxies we see, the stars, the planets, all of it exists only along the thin walls between these enormous bubbles of nothing. Now here is where it gets personal. Our galaxy does not sit at one of those dense intersections. Scientists have confirmed we live right next to a significant underdense region, and some researchers now argue we may be sitting inside a much larger void, one that spans roughly 2 billion light-years across. To put that in perspective, our entire galaxy is about 100,000 light-years wide. The void some scientists believe we inhabit is 20,000 times larger than our entire galaxy, from one side to the other. That changes everything about how we read the universe. When astronomers measure distances across space, they rely on how bright objects appear versus how bright they actually are. They measure how fast the universe is expanding. They build models of how matter is distributed. Every single one of those tools assumes we are standing in a representative patch of the universe, an average spot. Nothing unusual. But what if we are standing in a hole? What if every ruler we have ever used has been slightly warped by the fact that we live inside a region with less matter, less gravity, and a different expansion rate than the cosmic average? Our measurements would be off. Quietly, systematically off, in ways that would be almost impossible to detect without stepping back far enough to see the full picture. And here is the thing that should make you pause. We may not be able to step back far enough. We can only observe from one location. We cannot move outside the universe and look in. Every conclusion we have ever drawn about the cosmos, its age, its size, its fate, comes from measurements taken from right here, inside whatever structure surrounds us. Scientists discovered this problem slowly, almost accidentally. Nobody went looking for voids at first. They were mapping galaxies, just trying to understand where things were. And they kept finding these enormous regions where galaxies simply stopped appearing, blank patches in the three-dimensional map of the universe. Holes that seemed too big, too clean, too empty to fit neatly into the models cosmologists had built. That discomfort has never fully gone away. The void we may inhabit does not have sharp walls or a visible boundary. You cannot look out a window and see the edge of the emptiness. The transition from inside a void to outside one is gradual, spread across hundreds of millions of light-years, which means you could live your entire life, and humanity could exist for its entire history without ever suspecting the ground beneath the cosmos was not level. We may have been reading a tilted map this whole time, and the void right next door, that one has a name, and scientists confirmed it decades ago. There is a hole in the universe sitting directly beside our galaxy. Astronomers have mapped it, measured it, and given it a name. They call it the local void, and despite being one of the most significant structures in our immediate cosmic neighborhood, most people have never heard of it. The local void sits adjacent to our galaxy, beginning roughly where our nearest large galactic neighbors thin out, and stretching away into a region where almost nothing lives. Astronomers estimate it spans somewhere around 1 billion light-years in its largest dimension. Inside it, galaxies are rare, isolated, and unusual. The normal rules of galactic development barely apply there. You might expect a void that enormous to feel distant, abstract, somewhere far out in deep space, far removed from anything that matters to us. But the local void does something direct and measurable. It pushes us. Because a void contains less matter than the surrounding cosmic web, it exerts less gravitational pull on everything around it. The dense walls and filaments surrounding the void pull matter toward them. The void itself pushes, or more accurately, fails to pull, which in gravitational terms produces the same result. Our galaxy and everything around it is being nudged away from the local void and toward denser structures on the opposite side. Astronomers have measured this motion directly. Our galactic neighborhood is moving away from the local void at roughly 140 miles per second. That is a confirmed measurement, not a theory. We are being pushed across the universe by the simple absence of matter behind us. Think about what that means for a moment. The emptiness itself is shaping our trajectory through space. A hole in the cosmic web is steering our galaxy's path through time. And we had no idea this was happening until scientists began mapping the distribution of galaxies in 3 dimensions in the late 20th century. Before that mapping, we had no way to see the structure surrounding us. We could only see individual galaxies, not the architecture they were part of. It is like trying to understand a city by looking at individual bricks. Only when you step back and see the whole layout does the pattern become clear. When scientists built that 3-dimensional map of our cosmic neighborhood, the local void appeared immediately, a vast underpopulated region, clearly defined by the sudden drop in galaxy density along one side of our position in space. The data was unambiguous. Something enormous and nearly empty sits right next door. Now here is where the story gets more complicated. The local void is large, but some scientists argue it may be a smaller feature inside a much bigger structure. If the KBC void hypothesis is correct, and we will get to that in detail soon, then the local void is just one bubble inside a larger bubble, and we sit somewhere inside the larger one. A void within a void. The idea that emptiness can nest inside emptiness, that the universe builds its hollow architecture at multiple scales simultaneously, is one of the stranger implications of modern cosmology. And once you start looking for that nesting structure, you start finding it everywhere. But before we get to supervoids and nested emptiness, we need to go back to the moment when humans first stumbled onto cosmic voids by accident, because nobody planned to find them. They appeared in the data like a surprise no one was ready for. And when they appeared, they broke one of the most comfortable assumptions in all of cosmology. It was the late 1970s. A team of astronomers was doing something straightforward, plotting galaxies onto a 3-dimensional map. Take a galaxy, measure its distance, mark its position, repeat thousands of times. The goal was simple: build a picture of how matter is arranged in our cosmic neighborhood. Nobody expected the map to look strange. The prevailing assumption in cosmology at the time was that galaxies were distributed more or less randomly throughout space, with slight clustering here and there, but nothing dramatic. The universe was supposed to look roughly the same everywhere you pointed your telescope. Uniform, smooth. The map they built looked nothing like that. What emerged was a structure that stunned the team. Galaxies did not scatter randomly. They arranged themselves along thin filaments and flat sheets like soap bubbles pressed together. And between those sheets, between those filaments, there was almost nothing. Enormous regions of space, with virtually no galaxies at all. The first cosmic voids had been found. The discovery shook the field. If the universe had this kind of large-scale structure, enormous sheets and enormous holes, then the models used to explain how the universe evolved after the Big Bang were incomplete. The physics of structure formation needed a serious rethink. One of the most famous early void discoveries came in 1981, when a team studying a region of sky in the constellation Boötes found an underdense region so large it seemed almost impossible. The void they found spanned roughly 330 million light-years across. At the time, that was so extreme that many scientists simply refused to believe it. A structure that large should not exist if the standard models of cosmology were correct. The universe had not had enough time to produce something like that through normal gravitational processes. And yet, there it was. The debate that followed shaped the next 4 decades of cosmological research. Scientists began refining their models. They introduced cold dark matter, then adjusted the role of dark energy, then ran computer simulations trying to reproduce what they were seeing in the real universe. Some simulations worked. Others produced voids, but not quite as large or as empty as the ones astronomers kept finding. That gap between simulations and observations has never fully closed. Here is the part that matters for everything else we are going to discuss. The discovery of cosmic voids forced scientists to ask a question that sounds simple, but cuts to the core of cosmology. If the universe has enormous empty regions and enormous dense regions, how do we know where we are standing? How do we know that our local patch of universe, the region we use as our baseline for measuring everything else, is representative of the whole? The honest answer is that we do not know. We assumed it was. We built our models on that assumption. We measured the age of the universe, the rate of its expansion, the distribution of matter, all from this one location, trusting that it was an average spot. That trust has been eroding steadily since those first accidental maps were drawn. Because when scientists looked more carefully at the universe around us, they found something that suggested our location is anything but average. They found that the expansion of the universe appears to be faster in our neighborhood than it should be. And one of the leading explanations points directly at a supervoid we may be sitting inside. The name of that void is the KBC void, and the evidence for it is uncomfortable. Picture the darkest, most remote place you can imagine, a region of space where you could travel in any direction for 150 million light years and find almost nothing. No galaxies, no star clusters, no sign that matter ever settled there, just cold, dark, expanding emptiness. That place is real. Astronomers call it the Boötes void. Confirmed in 1981, after a team of scientists analyzed galaxy survey data, the Boötes void sits roughly 700 million light-years from us in the direction of the constellation Boötes. Its diameter is estimated at around 330 million light-years. To put that in terms, you can feel our entire galaxy stretches about 100,000 light-years from edge to edge. The Boötes void is roughly 3,000 times wider than that. If our galaxy sat at the center of the Boötes void, and you looked out in every direction with the most powerful telescopes ever built, you would see almost no other galaxies. The nearest galactic neighbors would sit on a wall of the void, hundreds of millions of light-years away. You would see a sky full of stars inside your own galaxy. But beyond that, a darkness stretching so far in every direction that it would feel like existing alone inside the universe. That isolation is hard to overstate. When the Boötes void was first announced, the response from the scientific community ranged from skepticism to outright disbelief. Standard cosmological models predicted that gravity and the early conditions of the universe should produce voids, yes, but voids of maybe 40 or 50 million light-years across. A structure 300 million light-years wide violated those predictions by a significant margin. One astronomer at the time reportedly said that if you found one more structure like the Boötes void, you would have to seriously consider whether the Big Bang model needed replacing entirely. Subsequent surveys confirmed the void was real, and more voids almost as large appeared in the data as surveys expanded. The Boötes void was not an error. The universe genuinely produces structures that large. But here is where the Boötes void gets even stranger. It is nearly empty, but nearly is doing important work in that sentence. A small number of galaxies exist inside it, roughly 60 confirmed as of recent surveys. Those galaxies are not clustered together the way galaxies usually are. They sit alone in the dark, widely spaced, evolving in almost complete isolation. They are orphans of the cosmic web, cut off from the network of filaments and sheets that most galaxies belong to. Scientists study those interior galaxies carefully because they represent a natural experiment. A galaxy growing inside a void receives almost no gravitational influence from neighbors, almost no disturbance from galactic collisions. It grows in silence, and the results show clearly in its structure and composition. Void galaxies tend to be bluer, younger looking, with more ongoing star formation than average. The quiet of the void actually seems to preserve them in a kind of extended youth. Now, the Boeta's void is enormous and scientifically significant. But the void some researchers believe we are living inside is in a completely different size category, larger, deeper, and with consequences that reach into every measurement we have ever made about the cosmos. That structure, and the specific tension it creates with our best cosmological data, is where our story accelerates. Cosmic voids do not appear suddenly. They grow, slowly, patiently. Over billions of years, gravity carves them out of the universe like an invisible sculptor working in reverse. To understand how a void forms, you have to go back to the earliest moments after the Big Bang. The universe at that point was almost perfectly uniform. Almost. Spread through that hot, dense, early soup were tiny quantum fluctuations, minuscule regions where the density was slightly higher or slightly lower than average. These differences were almost immeasurably small at first, but gravity is relentless. Regions that were slightly denser attracted nearby matter. More matter meant more gravity. More gravity pulled in still more matter. Over hundreds of millions of years, those slightly overdense regions grew into filaments and sheets. And the regions that were slightly underdense at the start, gravity abandoned them. Matter drained away from those areas, pulled toward the growing filaments on all sides. Left behind was emptiness, a void. The process feeds itself. As matter drains away from an underdense region, that region becomes less and less capable of holding on to the matter that remains. The gravity inside the void weakens further. Nearby matter on the edges gets pulled toward the dense walls rather than toward the void's interior. The void expands. Its walls grow denser. The contrast between full and empty sharpens over cosmic time. This is why voids today are so much larger and emptier than the voids that existed early in the universe's history. The universe has had over 13 billion years for this process to run. Gravity has had 13 billion years to drain the empty regions and pack the dense ones. Here is something that takes a moment to absorb. Voids are growing right now. They are actively expanding as you listen to this. Matter, along the edges of every void in the observable universe, is slowly migrating outward along filaments toward denser regions. The cosmic web is not static. It breathes. It tightens. The voids get more extreme with every passing billion years. In the far future, if the universe continues its current trajectory, voids will dominate even more completely than they do today. The cosmic web will grow increasingly sparse, its filaments stretched thinner and thinner as matter concentrates into fewer and fewer massive knots. But there is a twist in this process that scientists discovered relatively recently, and it involves the mysterious force that drives the universe's accelerating expansion: dark energy. Dark energy is pushing the universe apart at an accelerating rate. That acceleration means that at very large scales, gravity eventually loses its ability to pull structures together. Matter that has drifted too far apart cannot overcome the expanding space between it. So while gravity builds structure at intermediate scales, dark energy undermines structure at the very largest scales. The result is a race. Gravity builds the cosmic web. Dark energy slowly tears it apart, and voids sit at the intersection of both forces, expanding under the influence of dark energy, while their walls are sculpted by gravity. Scientists realized they could use voids as a measuring instrument for dark energy. The rate at which voids grow, how fast they expand, how empty they become. All of that encodes information about how much dark energy exists and how it behaves. Voids became cosmic laboratories, and one specific void is sitting at the center of the most heated debate in cosmology right now, because the numbers coming out of it do not match the numbers coming from anywhere else. In 2013, a team of astronomers published a paper that attracted serious attention and serious pushback in equal measure. They had analyzed the distribution of galaxies across a vast region of space surrounding our position in the universe. What they found was a systematic underdensity in every direction they looked. The researchers, Ryan Keenan, Amy Barger, and Lennox Cowie, whose initials give this structure its name, argued that we appear to sit inside a region where the density of galaxies and matter is roughly 20% lower than the cosmic average. This region, the KBC void, stretches roughly 2 billion light-years across. 2 billion light-years. That is a scale that does not have an easy comparison. If you traveled at the speed of light, the fastest anything can move through space. It would take 2 billion years just to cross this void from one side to the other, and we are sitting somewhere inside it. The evidence for the KBC void comes from galaxy counts. When you map the density of galaxies in every direction around us and compare that density to what the standard cosmological model predicts, you consistently find fewer galaxies than expected inside a roughly spherical region centered near our position. That underdensity is real and measurable. The scientific debate is about its precise size, its depth, and whether it is significant enough to affect our cosmological measurements. Here is why this matters far beyond just knowing what neighborhood we live in. Every measurement of the universe's expansion rate depends on distance. To measure how fast the universe expands, you need to know how far away things are. And to know how far away things are, you need to assume that the region around you is representative of the average universe. If you live inside a void, matter density around you is lower than average. Lower density means weaker local gravity. Weaker local gravity means the universe around you expands slightly faster than it does in denser regions. So if the KBC void is real, and we are inside it, every expansion rate measurement we have made from our location would be biased toward a slightly higher value than the true cosmic average. That bias is exactly the size needed to explain one of the most troubling puzzles in modern physics. There are two main ways to measure how fast the universe is expanding. One method looks at the early universe, analyzing the pattern of the cosmic microwave background radiation, the ancient light left over from just after the Big Bang. The other method looks at the local universe, measuring distances to nearby galaxies, using exploding stars and pulsating giant stars as calibrated distance markers. Both methods are carefully designed. Both have been checked and rechecked by independent teams, and they give different answers. The local measurement comes out higher than the early universe measurement. The gap between them has been named the Hubble tension, and it has resisted every simple explanation scientists have thrown at it. Living inside the KBC void offers a potential resolution. If our local expansion rate is inflated by our underdense environment, the local measurement would read too high compared to the true cosmic value. The tension between the two measurements would dissolve, but dissolving the tension that way introduces a different problem, a problem that gets stranger the deeper you look. Two teams of scientists, two completely different methods, two answers that should match but do not. This is the Hubble tension, and it has been quietly destabilizing cosmology for over a decade. The expansion rate of the universe is measured using a number called the Hubble constant. This number tells you how fast galaxies are moving away from each other for every unit of distance between them. It is one of the most fundamental numbers in all of cosmology. Get it right, and you can calculate the age of the universe, predict its future, and test every major theory about its evolution. Getting it right has turned out to be surprisingly difficult. The first method to measure it looks backward in time. Scientists analyze the cosmic microwave background, the oldest light in the universe, which was released roughly 380,000 years after the Big Bang. That ancient light carries an imprint of the early universe's density patterns. And from those patterns, you can calculate what the expansion rate should be today, assuming the standard cosmological model is correct. This method gives a value of around 67 kilometers per second per megaparsec. Or in simpler terms, for every 3 million light years of distance, galaxies are moving apart at roughly 42 miles per second faster. The second method measures the expansion directly, today, in our local universe. Scientists find stars and exploding stars that have predictable brightness, use them as distance markers, measure how fast nearby galaxies are receding, and calculate the expansion rate from scratch. This method gives a value closer to 73 kilometers per second per megaparsec, or roughly 46 miles per second per 3 million light years. The gap between those two values sounds small in everyday terms. In cosmology, it is enormous, and it has not shrunk as measurements have become more precise. It has stubbornly held, and in recent years the statistical confidence that this gap is real, and not just measurement error, has grown significantly. Multiple independent teams using multiple different measurement techniques have now confirmed the high local value. The early universe prediction consistently gives the lower number. Something is wrong somewhere, and nobody can agree on what. The standard explanations have mostly been ruled out. Measurement error cannot account for a discrepancy this persistent across this many independent studies. Calibration problems were the first suspects, but teams using entirely different calibration chains get the same results. The gap has survived every attempt to close it with better data. That leaves two broad categories of explanation. Either there is something wrong with the standard cosmological model, some new physics operating in the early universe, or today that changes how we interpret those measurements. Or there is something unusual about our specific location in the universe that makes our local measurements unrepresentative of the cosmic average. The KBC void falls into that second category. If we live inside a region with lower than average matter density, our local expansion rate is genuinely higher than the cosmic average. The early universe measurement captures the true cosmic rate. Our local measurement captures a locally inflated rate. The two numbers disagree because they are measuring different things. This explanation has serious support among some cosmologists. It also has serious critics. The debate is real, ongoing, and unresolved. And here is the uncomfortable implication sitting underneath all of it. If the void explanation is correct, then every distance measurement we have ever made in the local universe carries a systematic error we have only recently recognized. Our map of the cosmos is built on a foundation that may be tilted. What that tilted map means for the age and fate of the universe is even more unsettling. Imagine building a map of a country using a ruler that is slightly too short. Every distance you measure comes out slightly larger than reality. And because every other measurement depends on that ruler, every calculation you make from the map carries the same systematic error, compounding quietly as you go. Roads look longer. Cities look farther apart. Your sense of the entire country shifts by a consistent, invisible margin. That is the scenario cosmologists are now taking seriously for the universe. If we live inside the KBC void, our local measurement of the expansion rate is inflated compared to the true cosmic average. That inflation is built into the distance markers we use. The exploding stars and pulsating giant stars that we rely on to measure cosmic distances were calibrated using nearby objects, all of which are inside the same void we inhabit. The calibration chain we trust was built entirely within an underdense region. Every galaxy distance we infer using that chain would be slightly off, and from distances we derive everything else. The luminosity of distant objects, the age of the universe, the amount of dark energy, the geometry of space itself. A 20% underdensity in our local void, which is the approximate depth scientists estimate for the KBC void, could shift our local expansion rate by around 5 to 10% relative to the true cosmic value. That is roughly the size of the Hubble tension. The numbers fit. And if the numbers fit, then our best estimate of the universe's age, currently around 13.8 billion years, might be slightly off, perhaps by several hundred million years in one direction or another. Several hundred million years sounds enormous. In cosmic terms, it is a rounding error, but it changes the timeline of when the first stars formed, when galaxies matured, when conditions for life first arose in the universe. Every timestamp in cosmic history shifts together. And here is a detail that most discussions of this topic skip past. The void explanation for the Hubble tension does not just affect our measurement of distances, it affects our inference about dark energy. The amount and behavior of dark energy in the universe is calculated partly from how the expansion rate has changed over time. If our local expansion rate is systematically inflated, our picture of dark energy's strength and evolution could be distorted. Dark energy is already the most mysterious and least understood ingredient in the universe. We know it exists because of the accelerating expansion we observe. But its precise nature is completely unknown. If the expansion measurements are biased, our constraints on dark energy loosen. Possibilities that seemed ruled out become viable again. The void does not just warp our map of where things are, it potentially warps our understanding of what the universe is made of and what it is doing. Critics of the void explanation point out that a void as large and as deep as the KBC void would itself be difficult to explain within standard cosmology. Structures that size should be rare. Some simulations suggest a void of those proportions is statistically improbable, though possible. Others suggest the data could be interpreted differently, with the underdensity being real but shallower than originally claimed. The debate is ongoing. New surveys are gathering data. Stronger telescopes are mapping galaxy distributions with increasing precision. And in the middle of all this uncertainty, the oldest light in the universe carries its own clue. A cold patch on the ancient sky that may be the shadow of the largest known void ever identified. Roughly 380,000 years after the Big Bang, the universe cooled enough for atoms to form for the first time. Before that moment, space was so hot and dense that light could not travel freely. Photons constantly collided with free electrons, bouncing around in an opaque fog. When atoms formed, the fog lifted, light streamed outward in every direction. That light is still traveling. It has been crossing the universe for over 13 billion years. And when we point our most sensitive instruments at the sky, we detect it as a faint glow of microwave radiation coming from every direction simultaneously. Scientists call this the cosmic microwave background. It is the oldest observable thing in the universe, a photograph of the cosmos taken just after the lights came on. The cosmic microwave background is almost perfectly uniform in temperature. Almost. Across the entire sky, it sits at a temperature just below 3 degrees above absolute zero. But hidden inside that near uniformity are tiny temperature fluctuations, regions fractionally warmer or cooler than average. Those fluctuations are the imprint of the early universe's density variations, the same small clumping patterns that gravity would later amplify into galaxies, filaments, and voids. Scientists have mapped these temperature fluctuations with extraordinary precision. The pattern matches theoretical predictions well. The cosmological model built on these patterns, with its mix of dark matter, dark energy, and ordinary matter, reproduces much of what we observe in the universe today. But the map has anomalies. Certain features in the cosmic microwave background do not fit neatly into the standard model. One of the most discussed is a statistically unusual alignment of large-scale temperature patterns across the sky, sometimes called the axis of evil, by researchers who found its existence troubling. Another is a region of the sky that consistently appears cooler than surrounding areas by a small but measurable margin. That cold region sits in the direction of the constellation Eridanus in the southern sky. Its size spans roughly 1 billion light-years across the sky, as projected onto the ancient light. Its temperature is about 70 microkelvins below the average of the surrounding background, a tiny difference in absolute terms, but a significant statistical outlier given how uniform the background otherwise is. Scientists call it the cold spot. The cold spot has been known for over 2 decades and has been confirmed by multiple independent analyses. Its existence is not in dispute. What remains hotly debated is its cause. The most mundane explanation is statistical. In a map with as many data points as the cosmic microwave background, some cold regions will appear by chance. The cold spot may be nothing more than a rare statistical fluctuation, an unusually cold patch that happened to form without any extraordinary cause. But the numbers required for that explanation are uncomfortable. The probability of seeing a cold region of that size and depth by pure chance sits somewhere in the range of 1 in 50 to 1 in several hundred, depending on which analysis you trust. Rare, but possible. And there is a different explanation, one that connects the cold spot directly to the structure of the universe between us and the edge of the observable cosmos, an enormous supervoid. Light loses energy when it climbs out of a gravitational well, climb out of a dense region of space, and the photon emerges slightly cooler than it entered. This is a confirmed effect called gravitational redshift, and it applies everywhere in the universe. Now flip it. What happens when light passes through a void, a region with less matter and less gravity than average? As the light falls into the void, it gains a small amount of energy. As it climbs out the other side, it should lose that energy back. In a universe with a constant expansion rate, those two effects cancel perfectly. No net change. But we do not live in a universe with a constant expansion rate. Dark energy is accelerating the expansion. That changes everything. When a photon enters a void, the void is a certain size. By the time the photon exits on the other side, the void has grown larger because the universe is expanding faster over time. The gravity well the photon climbed out of is shallower than the one it fell into. The photon exits with slightly less energy than it had when it entered. Slightly less energy means slightly lower temperature. A photon that passed through an enormous void would arrive at our detectors fractionally cooler than surrounding photons. This mechanism has a name. Scientists call it the integrated Sachs-Wolf effect, specifically its late-time version. And if a supervoid of sufficient size sits between us and the cosmic microwave background in the direction of the cold spot, it would produce exactly the kind of temperature dip we observe there. In 2015, a team of astronomers announced they had found a candidate for that supervoid. Analyzing galaxy survey data in the direction of the cold spot, they identified a region with significantly fewer galaxies than surrounding areas, beginning roughly 1 billion light-years away from us and stretching outward. They called it the Eridanus supervoid. The Eridanus supervoid is confirmed as a real underdense region. Its existence is solid. What remains debated is whether it is large enough and deep enough to produce the full temperature dip seen in the cold spot. Early estimates suggested the void's size could produce only about 20% of the observed temperature decrease. Subsequent analyses using larger galaxy datasets have pushed that estimate higher, with some researchers arguing the void could account for a significant fraction of the cold spot's depth, and perhaps all of it, under certain models of dark energy. The debate comes down to the precise depth of the underdensity inside the supervoid. A void that is 20% less dense than average produces a different signal than one that is 30 or 40% less dense. Current surveys do not yet have the resolution to map the internal density profile of a structure 1 billion light-years away with enough precision to settle the argument. What makes this genuinely significant is the connection it draws. We may live inside a supervoid, and in the direction we look toward the oldest light in the universe, we may be seeing the shadow of another supervoid, even larger, sitting between us and the edge of the observable cosmos. Voids within voids. Empty regions stacked at multiple scales, stretching across the universe in ways our models are only beginning to capture. And the strangest proposed explanation for the cold spot does not involve voids at all. It involves a collision with something outside our universe entirely. The void explanation for the cold spot is scientifically conservative. A supervoid in the right place at the right depth could imprint a cold region on the cosmic microwave background through a well-understood gravitational mechanism. It stays comfortably inside accepted physics. But some scientists have proposed a different origin for the cold spot, one that requires stepping entirely outside the observable universe. The multiverse is a theoretical framework, and this is important to state clearly, in which our universe is one of an enormous or infinite number of universes, each existing in its own bubble of space, separated from the others by regions of still inflating space. This idea emerges from certain versions of inflationary cosmology, the theory describing the explosive expansion of space in the first fractions of a second after the Big Bang. If the multiverse is real, then our bubble universe exists alongside others. Those other universes would generally be causally disconnected from ours, separated by distances and expansion rates that make contact essentially impossible. Unless two bubble universes once collided, bubble universe collisions, if they occurred in the very early universe when bubbles were still forming and expanding, would leave physical signatures in the cosmic microwave background. The collision would send a shockwave through our universe's fabric, imprinting a circular pattern on the ancient light. The region of the collision would appear either warmer or cooler than the surrounding background, depending on the details of the collision geometry. The cold spot is roughly circular. It sits in the southern sky as a clearly defined cooler region, surrounded by a warmer ring. Some researchers have pointed out that this morphology fits the predicted signature of a bubble collision surprisingly well. This hypothesis remains speculative. Scientists have not found definitive evidence distinguishing a bubble collision signature from a statistical fluctuation or a supervoid. The circular shape alone is suggestive but not conclusive. Researchers have searched for additional predicted signatures of a bubble collision in the polarization patterns of the cosmic microwave background and have found results that are intriguing but inconclusive. What makes this hypothesis worth taking seriously is that it makes testable predictions. A bubble collision should produce a specific pattern, not just in temperature, but in how the ancient light is polarized. Future instruments measuring that polarization with greater sensitivity could potentially confirm or rule out the collision scenario. If it were confirmed, the implications would be staggering. A scar on the oldest light in the universe, left by a collision with another universe billions of years before Earth formed. Our cold spot would be a window into a reality larger than anyone has ever proved to exist. And yet, even inside this bold hypothesis, the void plays a role. Some theorists argue that the bubble collision would have created a region of lower density in our universe at the collision site, a void born from the impact itself. The supervoid and the bubble collision are connected in some models, with one producing or deepening the other. For now, the origin of the cold spot remains an open question. Scientists have multiple viable explanations and cannot yet separate them with existing data, but the tools to answer the question are being built right now. And what they reveal about voids, structure, and our place in the cosmos may force a reckoning with one of the oldest and most comfortable assumptions in all of science. Inside every major void in the observable universe, there are survivors. Galaxies that formed in the wrong place too deep inside an emptying region to escape toward the dense filaments where most galaxies cluster. They ended up stranded as the void expanded around them, left to evolve in near-total isolation for billions of years. Scientists call them void galaxies, and they have become one of the most valuable natural experiments in all of astronomy. A galaxy's character is shaped by its environment. In dense galaxy clusters, interactions are constant. Galaxies collide, merge, and strip gas from one another. Gravitational forces from neighbors distort their shapes. Streams of gas flowing along cosmic filaments feed them fresh material to form new stars. The chaos of a dense environment produces a wide variety of galaxy types and evolutionary paths. A void galaxy experiences almost none of that. Neighbors are hundreds of millions of light years away. Cosmic filaments do not thread through the void interior. Fresh gas from large-scale structure does not arrive on a regular schedule. A void galaxy grows up in silence, governed almost entirely by its own internal physics. The result is striking. Void galaxies tend to be smaller on average than galaxies in dense regions, because they have had fewer mergers to grow from and less external gas to feed on. They tend to be bluer, meaning they contain more young, hot, recently formed stars. They have higher rates of ongoing star formation relative to their size, suggesting they are still actively building themselves, still in what astronomers think of as an extended adolescence. In dense cluster environments, most large galaxies have completed the bulk of their star formation and entered a quieter phase. Void galaxies appear to be running on a different timetable. The quiet of the void preserves their star-forming activity for longer. One particularly striking finding involves the shapes of void galaxies. In dense environments, gravitational interactions between galaxies frequently disturb their structure, producing irregular shapes, asymmetric features, and disrupted spiral arms. Void galaxies tend to have cleaner, more regular shapes, undisturbed spirals, rounder ellipticals. Their structure reflects their undisturbed lives. Astronomers studying void galaxies found something else unexpected. The relationship between a galaxy's mass and its star-forming activity follows slightly different rules inside voids. The same mass of galaxy, given the same amount of gas, converts that gas into stars more efficiently in a void environment than in a dense one. The mechanism behind this is still being investigated, but it appears that the lack of environmental disruption allows star formation to proceed more smoothly and completely. This has implications for understanding galaxies everywhere. If environment shapes evolution so profoundly, then our existing models of how galaxies form may be systematically biased, because most well-studied galaxies live in relatively dense environments where we have the easiest time observing them. The physics of galaxy formation inside voids may be closer to the simplest, most fundamental version of that process, without the complications added by crowded neighborhoods. Studying void galaxies gives astronomers something rare, a look at what a galaxy does when left entirely to its own devices. And the void itself is doing something to those galaxies beyond just leaving them alone. The void is actively pushing them outward. And that pushing mechanism, when scientists understood it fully, revealed something strange about how emptiness exerts force. Gravity pulls. That is one of the most basic statements in physics. Mass attracts mass. Planets orbit stars. Galaxies cluster together. The universe bends towards density, So it takes a moment to absorb the fact that cosmic voids push galaxies outward, not because they contain some exotic repulsive force, because of what they lack. Imagine you are standing on a flat surface, surrounded by a dense crowd of people on every side except one. On that one side, the crowd thins out and then disappears entirely. The people on the other sides are pressing in, but the empty side offers no resistance, no push in return. The net result is that you drift toward the empty side, carried by the imbalance. Cosmic voids work on a similar principle, scaled up to the size of galaxy superclusters. A galaxy sitting on the edge of a void has dense structure on one side, the cosmic filaments and walls surrounding the void, and nearly empty space on the other. The dense side exerts a gravitational pull. The void side exerts almost none. The galaxy experiences a net gravitational push, or more precisely, a net pull toward the dense side, which from the galaxy's frame of reference looks like a push away from the void. As voids grow and empty out, this effect strengthens. Galaxies on the void's edges accelerate away from its center. The void expands partly through this active mechanism of evacuating its own boundaries. It drives matter out of itself into the surrounding cosmic web. This process is called void evacuation, and scientists have measured it directly in our cosmic neighborhood. The local void, the confirmed underdense region adjacent to our galaxy, is doing this to us right now. Our galaxy and the entire local group are moving away from the local void at around 140 miles per second, carried outward by the gravitational imbalance between the void behind us and the denser structures ahead. What surprised researchers when they modeled this process carefully is how closely it mimics the effect of dark energy on large scales. Dark energy drives the accelerating expansion of the universe. It pushes space apart at every point, causing distant galaxies to recede from us faster and faster over time. The effect is uniform, acting everywhere in the universe simultaneously. Void evacuation is local. It acts on galaxies near the boundaries of specific voids, not everywhere, but the resulting motion, galaxies accelerating away from underdense regions towards denser ones, looks superficially similar to dark energy-driven expansion when viewed from inside the void. Some theorists have explored whether a universe full of large voids could mimic certain aspects of dark energy's observed effects without dark energy actually existing as a separate ingredient. These models, sometimes called back-reaction cosmologies, suggest that the irregular structure of the universe, all those holes and walls and filaments, alters the average expansion rate in ways that look like dark energy, but emerge purely from the lumpiness of matter distribution. Most mainstream cosmologists find this explanation insufficient on its own. The evidence for dark energy from multiple independent lines of observation appears robust, but the idea that voids contribute to and complicate our measurement of dark energy's behavior is taken seriously, because voids and dark energy are deeply fundamentally connected, and understanding one requires grappling with the other. Dark energy is the most abundant ingredient in the universe. Scientists estimate it makes up roughly 68% of everything. Ordinary matter, every star, planet, gas cloud and galaxy, accounts for only about 5%. Dark matter fills in much of the rest. But dark energy has never been detected directly. Its existence is inferred entirely from its effects, specifically from the fact that the expansion of the universe is accelerating, when gravity alone would be expected to slow it down. What dark energy actually is remains completely unknown. The leading candidate is a property of space itself, a constant energy density built into the fabric of the universe. Other proposals involve dynamical fields that evolve over time, changing their strength and behavior as the universe ages. Distinguishing between these possibilities requires extremely precise measurements of how the expansion rate has changed throughout cosmic history. Cosmic voids offer a way to make those measurements, because voids grow, and the rate at which they grow depends directly on the competition between gravity and dark energy. In a universe with more dark energy, space expands faster, and voids grow faster. Their walls spread apart more quickly. Their interiors empty out more completely. In a universe with less dark energy, or with dark energy that behaves differently, voids grow at a different rate, reach different sizes, and achieve different levels of emptiness. By measuring the actual sizes and emptiness profiles of voids across cosmic history, and comparing those measurements to model predictions, scientists can constrain the nature of dark energy with impressive precision. This approach has real advantages over other dark energy probes. Voids sample a different regime of the universe than galaxy clusters, or Type 1a supernovae, the exploding stars used as cosmic distance markers. Voids probe the low-density regions where dark energy's influence is comparatively stronger, since gravity is weaker in those regions and the competition between the two forces plays out more visibly. Researchers have built catalogs of thousands of voids from galaxy survey data, measuring their sizes, shapes, and density profiles, then comparing those statistics to predictions from cosmological models. The results have been consistent with the standard model of cosmology, but have also placed increasingly tight constraints on dark energy's equation of state, the precise mathematical relationship between its pressure and its energy density. Here is something that adds an extra layer to this picture. If we live inside the KBC void, our position inside an underdense region means we are embedded in exactly the kind of environment where dark energy's effects are most pronounced. Our local universe may be a slightly extreme version of void physics, with dark energy having had a stronger relative influence here than in denser regions of the cosmos. That could mean the acceleration of expansion we observe locally is running slightly hotter than the cosmic average. Our measurements of how fast expansion is accelerating, and therefore our constraints on dark energy's strength, may carry a subtle but real void location bias. Dark energy is already the biggest mystery in physics. The possibility that our measurements of it are influenced by our unusual location inside a supervoid makes that mystery slightly more complicated and significantly more interesting. And the evidence for our unusual location keeps accumulating from multiple directions. Some of the strongest clues are not found in galaxies or dark energy measurements, but in the oldest light in the universe, specifically in patterns in that light that should be random but are not. The cosmic microwave background should be random. At the finest scales, it is. The tiny temperature fluctuations that map onto galaxy-scale structures look exactly like the statistical noise expected from quantum fluctuations in the early universe. Scientists have analyzed those patterns in extraordinary detail and found excellent agreement with theory. But at the very largest scales, something unexpected appears. When researchers analyzed the large-scale temperature patterns in the cosmic microwave background, they found that certain features align with each other and with the plane of our galaxy in ways that seem statistically improbable. The largest temperature fluctuations in the ancient light, features that span the entire observable sky, share an orientation. They appear to point in the same direction. Cosmologists refer to this alignment as the axis of evil. The nickname reflects how unwelcome the discovery was, because a preferred direction in the ancient light violates a central assumption of cosmology. The cosmological principle states that the universe looks the same in every direction when viewed at large enough scales. No direction in space should be special. The cosmos should have no preferred axis, no favored orientation, no built-in asymmetry at the largest scales. It should be, in the technical language, statistically isotropic. The axis of evil appears to break that assumption. Several independent teams analyzing separate datasets have confirmed that the alignment is real in the data. The debate concerns its cause and its significance. One explanation is observer bias. Our galaxy emits microwave radiation of its own, which scientists must subtract from the raw cosmic microwave background data before analyzing it. If that subtraction is imperfect, residual contamination from our galaxy could create apparent alignments that are not real features of the ancient light. Scientists have worked hard to correct for this, and while they have reduced the potential contamination, they cannot fully rule it out. Another explanation involves systematic errors in the instruments used to map the ancient light. But multiple instruments, including 2 separate space missions, have produced consistent results. The third explanation is the one that cosmologists find most provocative. The large-scale alignments in the ancient light may be real features of the universe, reflecting a genuine asymmetry that was present from the very beginning. If that is the case, the cosmological principle fails at the largest scales, and the universe has a preferred direction built into its structure. What would cause such a direction? Possibilities include exotic physics in the very early universe, perhaps a period of anisotropic expansion, or the influence of a primordial magnetic field threading through the young cosmos. Some theorists have connected it to the multiverse scenario, where the geometry of bubble nucleation could imprint a directional signature on the early universe. Others have connected it to our large-scale environment. If we live inside a supervoid, and that void has a preferred elongation or orientation, it could subtly affect how we interpret the cosmic microwave background data, introducing an apparent alignment that reflects our local structure, rather than the universe at large. The axis of evil remains unresolved. It may be a measurement artifact, it may be cosmic noise, or it may be the first hint that the universe is built differently from the inside than the theory we have been using to describe it would predict. And there is another asymmetry in the universe, a confirmed one, that points in a specific direction across the entire observable sky, adding another layer to this growing picture. As our galaxy moves through space, the universe should look slightly different depending on which direction we face. This is a real effect, called the kinematic dipole, and it is well understood. When you move towards something, the light from it appears slightly blue shifted, meaning its wavelength is compressed, and it looks slightly brighter. When you move away from something, the light appears slightly red shifted, looking slightly dimmer. Our motion through the universe produces a faint gradient across the sky, brighter in the direction we are heading, and dimmer behind us. Scientists have measured this kinematic dipole in the cosmic microwave background for decades. It gives a precise measurement of how fast our galaxy is moving relative to the average background of the universe, and in which direction. Recently, researchers applied the same logic to a completely different dataset. Instead of looking at the ancient microwave light, they looked at distant radio galaxies and quasars, extremely bright and distant objects spread across the sky. By mapping how the brightness and number density of those objects vary across different directions, they expected to see the same dipole signature, the same faint asymmetry produced by our motion through space. What they found was a larger dipole than expected. The asymmetry in the distribution of distant galaxies and quasars is roughly twice as large as the kinematic dipole measured from the cosmic microwave background. If both measurements are correct, they are telling different stories about our motion, and two different measurements of the same quantity should agree. This discrepancy, first highlighted in multiple studies published over the past decade, has attracted serious attention. Several independent teams, using different datasets and different analysis methods, have confirmed that a real tension exists between the two dipole measurements. The standard kinematic explanation cannot easily account for the larger dipole in the distant source catalogs. Our galaxy is not moving twice as fast as the cosmic microwave background suggests. Something else is contributing to the observed asymmetry. Possible explanations include large-scale structure effects. If the distribution of matter in the universe is genuinely asymmetric at scales larger than we have mapped in detail, that asymmetry would affect the distribution of observed galaxies across the sky. We would see more galaxies in one direction simply because there is more matter in that direction at scales we have not fully accounted for. This connects directly to the possibility that the cosmological principle fails. If the universe has genuine large-scale asymmetries, directions with more or less matter built into its structure at the billion light-year scale, then our sky would look different depending on which direction we face. Not just because of our motion, but because the universe itself is structured differently in different directions. The dipole anomaly adds to a growing list of large-scale anomalies in cosmological data. Each one individually has a mundane potential explanation: statistical noise, measurement error, incomplete modeling of our local environment. But the accumulation of anomalies, the Hubble tension, the cold spot, the axis of evil, the dipole discrepancy, begins to feel like a pattern. And patterns point somewhere. They point to a source. In this case, they may all be pointing to the same source: our location, the void we inhabit. The underdense region that surrounds us tilts our measurements and quietly shapes everything we think we know about the universe at the largest scales. And the evidence for how that void shapes our most fundamental measurements is about to get significantly more specific. Every major calculation in cosmology rests on a single foundational assumption, an assumption so central that questioning it feels like pulling at a thread that holds the entire field together. The cosmological principle states that the universe is homogeneous and isotropic at large enough scales. Homogeneous means it has the same average density and composition everywhere. Isotropic means it looks the same in every direction. Together, these two properties mean that no location in the universe is special. Every observer, wherever they sit, sees the same average universe. This principle is not just a philosophical preference. It is a mathematical necessity for the equations describing cosmic evolution to be solvable in any practical sense. Without it, you cannot write down a single expansion rate for the universe, because different regions would expand at different rates. You cannot calculate a single age for the universe, because the rate of cosmic evolution would vary by location. You cannot assume that measurements made here apply elsewhere. The cosmological principle makes cosmology possible, and it emerged not from observational proof, but from simplicity and symmetry. It was reasonable. It seemed right. The observational evidence has been largely supportive. At scales above roughly 300 million light-years, the universe does look broadly similar in different directions and at different distances. The cosmic microwave background is almost perfectly uniform across the entire sky. The large-scale structure, when averaged over large enough volumes, appears statistically consistent with homogeneity, but several cracks have appeared. The Hubble tension shows two measurement methods giving different answers for the same fundamental quantity, a result that is hard to explain without either new physics or an inhomogeneous universe. The cold spot shows a temperature anomaly in the ancient light that may require a supervoid to explain, a structure that challenges standard predictions for how uniform the universe should be. The axis of evil shows apparent large-scale alignments in the ancient light that should be random if the universe is truly isotropic. The dipole anomaly shows the distribution of distant galaxies appearing asymmetric at a level that exceeds what our motion alone can explain. Each of these anomalies has been individually challenged. None of them is definitively proven to require a failure of the cosmological principle, but the cumulative picture is making a growing number of cosmologists uncomfortable. A 2022 analysis, published by a large team examining distant radio sources, concluded that the evidence against the cosmological principle at certain scales had reached a level of statistical confidence that was difficult to dismiss as chance. Other teams disputed the methodology. The debate continues at conferences and in preprint archives. If the cosmological principle breaks down, the consequences extend far beyond cosmology. Every branch of theoretical physics that borrows cosmological parameters to set boundary conditions for its equations would need to be revisited. The values plugged into models of particle physics, quantum gravity, and the long-term future of the universe all depend on those parameters. And at the heart of the question is our location. If we live inside a supervoid, we occupy a region that is by definition not representative of the average universe. We are looking out from a biased vantage point, measuring a universe that looks different from here than it does from a typical location. The cosmological principle may be mostly correct, failing only subtly and only at the very largest scales. Or it may be significantly wrong, and our entire cosmic map may need to be rebuilt from a different vantage point. The tools to find out are being assembled right now, and what they discover may be the most consequential measurement in the history of science. Our galaxy is moving. Every galaxy moves. But our galaxy is moving towards something specific, something massive, something that sits almost perfectly hidden behind the densest part of our own galaxy's disk, obscured by billions of stars and clouds of gas and dust that block our view in that direction. Scientists call it the Great Attractor. The discovery came gradually. In the 1970s and 1980s, astronomers mapping the motions of galaxies in our local universe noticed something puzzling. Hundreds of galaxies in our neighborhood were not moving in random directions as expected. They were streaming, flowing together, all heading toward a specific region of sky in the direction of the constellations Centaurus and Norma. Our galaxy was part of that flow. Something in that direction was pulling, something with an enormous gravitational reach. The problem is that the region of maximum interest sits directly behind the zone of avoidance, the band of sky blocked by our own galaxy's plane. Dust and stars in our galaxy absorb and scatter the light from anything behind them in that direction, making it nearly impossible to observe in optical wavelengths. Astronomers turn to radio waves and infrared light, which can penetrate the dust more effectively. What they found, piece by piece over the following decades, was a concentration of matter centered roughly 250 million light-years away. A massive galaxy cluster called the Norma cluster sits near the heart of the attractor region, surrounded by a web of filaments and additional clusters stretching across a volume hundreds of millions of light-years wide. The gravitational pull of this concentration is real and measurable. It is contributing to the motion of our galaxy, our local group, and hundreds of surrounding galaxies, all flowing in the same direction at hundreds of miles per second. But here is where the story complicates itself in an important way. When scientists finally mapped the Great Attractor region in detail and calculated its mass, they found a problem. The mass they could account for was real and significant, but it was not quite enough to explain the full velocity of the galaxies streaming toward it. Something else was contributing to the flow. Researchers looked deeper and found that our local flow is part of an even larger pattern. Thousands of galaxies across a volume spanning over 500 million light-years all appear to be moving in a coherent direction. Not just toward the Great Attractor, but toward a more distant concentration of structure in the direction of the Shapley supercluster, one of the most massive known collections of galaxies within the observable universe. Our galaxy is being pulled from at least two directions simultaneously by overlapping gravitational influences operating at different distances and scales. And here is the detail that connects back to everything we have discussed. The motion of our galaxy away from the local void and toward the Great Attractor and Shapley supercluster cannot be fully separated. The push from the void behind us and the pull from the density ahead of us are two parts of the same gravitational story. We are being squeezed out of emptiness and drawn toward mass. Scientists have a name for the entire structure that organizes this flow, and its discovery redrew our understanding of where we actually live in the cosmic web. In 2014, a team of astronomers published a paper that redrew the map of our cosmic address. Using a new technique to analyze galaxy motions across our local universe, they traced the flow lines of thousands of galaxies, following where each one was gravitationally drifting, and used those flows to define the boundaries of our home supercluster. What they found was a structure they named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea spans roughly 500 million light-years across. It contains the mass equivalent of roughly 100 million billion stars. Our galaxy sits near its outer edge, on the fringes of a structure that organizes hundreds of thousands of galaxies into a single gravitational watershed. The key insight behind Laniakea was using galaxy velocities rather than galaxy positions to define structure. Galaxies in the same supercluster all flow gravitationally toward a common low point, a region of maximum density at the center. By tracing which galaxies drain toward which gravitational basin, the team could draw boundaries between superclusters, the same way watershed maps draw boundaries between river drainage systems. Our galaxy and all its neighbors drain toward the interior of Laniakea, toward a central concentration of mass called the Great Attractor region. Every galaxy inside Laniakea's boundary is part of the same gravitational watershed, flowing inward, even if many of them will never actually reach the center, because the overall expansion of the universe is carrying them apart faster than gravity can pull them together. Laniakea is the largest confirmed structure our galaxy belongs to, and its discovery forced an immediate and important question. What lies outside its boundaries? Surrounding Laniakea are other superclusters, Perseid Pisces to one side, Coma to another, and the vast Shapley concentration pulling on our entire region from a greater distance. Laniakea itself appears to sit at the intersection of several cosmic filaments, threads of matter connecting it to the broader cosmic web. But there is something about Laniakea's immediate environment that has attracted increasing scientific attention in recent years. The region surrounding Laniakea, the larger volume in which it sits, appears to be somewhat underdense compared to the cosmic average. The supercluster itself is a dense structure, but it may be embedded within or adjacent to the broader underdensity of the KBC void. This creates a nested picture. Our galaxy sits near the edge of Laniakea. Laniakea sits inside or adjacent to the local void on one side, and possibly within the broader KBC void at a larger scale. The supervoid itself is bounded by denser structures like Shapley and the Perseus Pisces supercluster. We are nested inside layers of structure, each scale revealing a different aspect of our cosmic environment, each layer potentially introducing a different bias into our measurements. And the deeper researchers look, the more layers they find, because the question of whether Laniakea itself sits inside a larger underdense basin does not yet have a clean answer. New surveys are mapping the universe at greater distances and with better galaxy density resolution than ever before. And what those surveys are beginning to suggest is that the architecture of our cosmic neighborhood is stranger and more layered than the 2014 discovery captured. The tools being built to answer that question are extraordinary, and one of them may settle the debate about the KBC void, the Hubble tension, and our position in the cosmos within the next decade. The universe builds structure at every scale simultaneously. Planets orbit stars. Stars cluster into galaxies. Galaxies group into clusters. Superclusters link into the cosmic web. The same nested logic applies to emptiness. Small voids, spanning tens of millions of light years, sit inside larger voids spanning hundreds of millions. Those larger voids may themselves occupy underdense regions within supervoids spanning billions of light years. Emptiness, like structure, repeats at multiple scales, each layer shaped by the same gravitational physics, operating over different timescales and distances. This nesting was predicted theoretically before it was confirmed observationally. Computer simulations of the universe, run with dark matter and dark energy and the initial conditions measured from the cosmic microwave background, consistently produce a hierarchical void structure. Small voids merge over time as matter drains from both of them, creating larger voids. Those larger voids continue to evacuate and merge on even longer timescales, building supervoids. The process is slow. Small voids form first, carving out their interiors over hundreds of millions of years. Larger voids require billions of years to develop. At the scale of the KBC void, if it exists as described, you are looking at a structure that has been growing since the universe was a fraction of its current age. Scientists have found observational evidence for this hierarchy. Galaxy redshift surveys, which map three-dimensional positions of millions of galaxies, reveal small voids nested within larger underdense regions, both within the larger framework of the cosmic web. The pattern emerges clearly from the data once you know what to look for. Here is what makes the nested void picture genuinely unsettling for cosmology. If emptiness is hierarchical, then the question of whether we live inside a void does not have a simple yes or no answer. We may live inside a small void, which sits inside a medium void, which sits inside the KBC supervoid, which itself sits inside a broader underdense basin, at an even larger scale. At each level, our measurements could be slightly biased. Small voids produce small biases, larger voids produce larger ones. The cumulative effect of sitting inside multiple nested underdense regions at different scales could be significant, and disentangling those effects from the true cosmic average is extraordinarily difficult. The deepest layer of this hierarchy is essentially impossible to observe directly. A void spanning several billion light years would be nearly impossible to confirm using current techniques, because mapping galaxy density accurately at those distances requires galaxies bright enough to see across billions of light years, and the sampling becomes sparse enough that detecting a subtle underdensity becomes statistically very challenging. But simulations give us a clue. They show that in a universe like ours, supervoids spanning 1 to 2 billion light years appear with some regularity. They are rare, but expected. Finding ourselves inside one would be unusual, but statistically plausible. And here is a detail worth holding on to. The nested void structure means there may be no perfectly representative location in the observable universe. Every observer sits somewhere in the cosmic web, either in a void or on a filament, or in a cluster. No spot is truly average. The cosmological principle asks us to pretend otherwise, to assume our location is typical, but the structure of the universe suggests typical may not exist in any precise sense. Somewhere in this web of nested emptiness, future telescope surveys are hunting for the boundaries of these structures, and the first results are already arriving. The question of whether we live inside a supervoid is observationally testable. That is what separates it from speculation. Scientists know exactly what they need to measure. the three-dimensional distribution of galaxies across billions of light years, with enough density and precision to map underdense regions at the scale of the KBC void and confirm or refute its existence. Two instruments stand at the forefront of that effort. The Vera Rubin Observatory, located in Chile, began science operations recently and will spend a decade photographing the entire southern sky repeatedly. Over that decade, it will build a catalogue of billions of galaxies, tracking their positions, distances, and in many cases, their motions. The sheer volume of data it will produce is unprecedented in ground-based astronomy. Scientists will use that catalogue to build three-dimensional maps of the cosmic web with resolution and depth that were completely impossible using previous surveys. For the void question specifically, Rubin's data will allow researchers to measure galaxy density profiles across volumes spanning hundreds of millions to billions of light years, with enough statistical power to detect underdensities at the depth and scale proposed for the KBC void. If the supervoid is real and has the properties the original team claimed, Rubin's data should confirm it within a few years of full operation. The Euclid Space Telescope, launched by the European Space Agency in 2003, is pursuing a complementary approach. Euclid maps galaxies across a wide swath of sky, reaching to extreme distances, billions of light years away. Its goal is to measure the large-scale structure of the universe with precision sharp enough to constrain dark energy's behavior and test the cosmological principle directly. Euclid's void catalogue will be transformative. By mapping voids across different epochs of cosmic history, from the nearby universe to the distant universe billions of years in the past, researchers can trace how voids have grown over time and compare that growth to theoretical predictions. If the growth rate of voids disagrees with what standard cosmology predicts, that discrepancy will point toward new physics, whether that means modified dark energy, failures of the cosmological principle, or something else entirely. Together, Rubin and Euclid will produce the most comprehensive map of cosmic structure ever assembled. Within a decade, scientists will have data capable of answering several of the outstanding questions we have covered. The reality and depth of the KBC void, the source of the Hubble tension, the large-scale isotropy of the universe, and the growth history of voids across cosmic time. The answers may be clarifying and comfortable, confirming that standard cosmology is broadly correct and that our local environment is unusual, but not drastically biased. Or the answers may force a reckoning with assumptions that have held for decades. And there is a third possibility. The data from these instruments could reveal something nobody predicted, a new anomaly, or structure that raises questions none of the current theories have prepared us to answer. The history of cosmology suggests this third option is always the most likely, because every time we have built a more powerful instrument and looked at the universe with greater precision, we have found something unexpected. The cosmic microwave background revealed the axis of evil. Galaxy surveys revealed supervoids that challenged structure formation models. Measurements of the expansion rate revealed the Hubble tension. The next generation of instruments will not just answer questions, they will ask new ones. Dark matter does not emit light. It does not interact with electromagnetic radiation in any way we can detect directly. We know it exists because of its gravitational effects on galaxies, on galaxy clusters, and on the large-scale structure of the universe. But its fundamental nature, what it actually is at the particle level, remains completely unknown despite decades of searching. Most dark matter searches focus on detecting dark matter particles directly, using underground detectors shielded from cosmic radiation, or indirectly by looking for the products of dark matter particles annihilating each other in dense regions like the centers of galaxies or galaxy clusters. But cosmic voids offer a completely different approach to constraining dark matter, and in some ways, a more powerful one. The way voids grow depends on dark matter. Dark matter provides the gravitational scaffolding that shapes the cosmic web. The distribution of dark matter in the early universe determined where filaments would form, where clusters would concentrate, and where voids would expand. Different dark matter models predict subtly different void statistics, how many voids of each size should exist, how deep they should be, how their walls should be structured. The most widely accepted model involves cold dark matter, particles that were moving slowly compared to the speed of light in the early universe. Cold dark matter produces a specific type of cosmic web structure with small-scale clustering, dense filaments, and voids that grow in a particular way. Alternatives exist. Warm dark matter would consist of particles moving faster in the early universe, which would wash out small-scale structure. The cosmic web produced by warm dark matter would look different at small scales, with fewer small voids and smoother void interiors. Fuzzy dark matter, proposed to consist of extremely light particles with quantum wave behavior at galactic scales, would produce yet another signature in void structure. By measuring the detailed statistics of voids from large galaxy surveys, scientists can distinguish between these models: the number of small voids versus large voids, the sharpness of void walls, the internal density profiles of voids. All of these statistics carry fingerprints of the underlying dark matter model. This approach has an advantage over direct detection experiments. It does not depend on any assumed interaction between dark matter and ordinary matter beyond gravity. Whatever dark matter is, it must respond to gravity. Its gravitational effects on the cosmic web are unavoidable. Voids are therefore a dark matter probe that remains valid even if dark matter turns out to be something completely exotic that would never trigger a particle detector on Earth. Recent void catalogues from galaxy surveys have already placed meaningful constraints on dark matter properties, ruling out certain warm dark matter models and placing limits on how light or how interacting dark matter particles can be. As the Rubin Observatory and Euclid dramatically expand those void catalogues, the dark matter constraints will tighten significantly. Within a decade, void statistics may provide the strongest observational limits on dark matter's fundamental properties available from any source. The emptiest places in the universe, regions we might have assumed were scientifically boring, are turning out to be among the most information-rich environments in the cosmos. And the implications of that information extend beyond dark matter and dark energy into a question that feels almost personal. Could voids be the reason life exists? The universe is a violent place. Gamma-ray bursts release more energy in a few seconds than our star will emit across its entire lifetime. Supernovae scatter lethal radiation across thousands of light years. Supermassive black holes at the centers of active galaxies pump out jets of high-energy particles that sterilize everything along their path. Galaxy collisions trigger chaotic bursts of star formation, flooding regions with radiation. In dense regions of the universe, where galaxies cluster together in gravitational knots, these events are common. Galaxies interact constantly. Black holes merge and flare. Stellar populations churn through generations rapidly. The environment is energetically extreme. In a void, the situation is fundamentally different. Void galaxies evolve in near-total isolation. Their central black holes tend to be quieter, with fewer mergers to trigger accretion events and fewer companion galaxies to interact with. Stellar populations evolve at a gentler pace. Gamma-ray bursts are rarer in the lower star formation rate environments, characteristic of isolated void galaxies. The overall radiation environment inside a void galaxy, especially at the outskirts where star formation and black hole activity are minimal, may be significantly calmer than in a cluster galaxy. Calmer means safer for the development of complex chemistry and biology. This is a speculative line of reasoning, firmly in the territory of astrobiology, rather than confirmed cosmology. But it rests on real observations about how environment affects galaxy properties, and it raises a question that sits at the intersection of cosmic structure and the origin of life. If the KBC void is real, and if we genuinely inhabit an underdense region of the universe, our position inside a void may be partly responsible for the conditions that allowed Earth to exist at a habitable distance from a stable star, in a galaxy that has not been recently disrupted by a major merger, in a cosmic neighborhood free from the most extreme radiation environments. The anthropic principle, the idea that our observations of the universe are filtered by the fact that we exist and are here to observe, would predict exactly this. Observers capable of asking where they live would tend to find themselves in environments compatible with their existence. Voids may select for stability, and stability may select for life. There is an additional factor. Galaxies inside voids contain fewer heavy elements on average than galaxies in dense environments, because they have had fewer stellar generations to build up those elements through nuclear synthesis. But a specific subset of void galaxies, those that formed slightly earlier, or that have had enough stellar generations, can reach the metallicity levels needed for rocky planet formation. Our galaxy appears to be in that subset. It has enough heavy elements to build rocky planets, enough stability to avoid frequent disruptions, and enough time to allow complex chemistry to develop. Whether those conditions required a void location is unknown, but the correlation between void environments and stable, slowly evolving galaxies makes the connection worth investigating. The possibility that life is most likely to arise in the quiet periphery of the cosmic web, inside the vast empty bubbles that dominate the universe's volume, would be a striking conclusion. The emptiest places in the universe might be the most life-friendly ones, but what if tomorrow we confirmed that all of this was real, that we are definitively inside a supervoid, that the cosmological principle breaks down at large scales, that our measurements have been systematically biased? What would actually change? Imagine the announcement came through, a comprehensive analysis from the Rubin Observatory and Euclid, combined, confirmed by independent teams, delivered at a major cosmology conference. We live inside the KBC void. The underdensity is real. It spans 2 billion light-years, and its depth is sufficient to explain the Hubble tension and several related anomalies. What changes? The first and most immediate consequence would be a revision of the locally measured expansion rate. The true cosmic expansion rate would be recalculated, pulling back toward the value derived from the cosmic microwave background. The Hubble tension would dissolve, replaced by a coherent picture in which our local measurements were simply running fast because of our underdense environment. That sounds like a clean resolution, but it cascades. Every distance we have measured in the local universe, using the expansion rate as a calibration step, would need to be revised. The distances to nearby galaxy clusters, to the voids surrounding us, to the large-scale structures we have mapped in detail, all would shift. Not dramatically in most cases, but by a consistent, systematic amount tied to the depth of the void and how much it inflates our local expansion rate. From corrected distances come corrected luminosities. If things were actually closer than we thought, they are also intrinsically less bright than we thought. A range of astronomical objects we use as calibrators would need their standard candle brightnesses recalibrated. The chain of distance measurements that underpins all of observational astronomy would require a careful, systematic audit. The age of the universe calculation would also shift. The age we currently infer, around 13.8 billion years, comes from combining the expansion rate with measurements of the universe's geometry and composition. A lower true expansion rate implies a slightly older universe. The revision might amount to hundreds of millions of years. In absolute terms, that is a significant rewriting of the cosmic timeline. The implications for dark energy would be equally significant. Our current best estimate of dark energy's density and equation of state comes partly from local expansion measurements. Correcting those measurements for the void environment would change our constraints on dark energy, potentially opening up parameter space for models that were previously considered ruled out. The standard model of cosmology, called lambda CDM for its inclusion of a cosmological constant and cold dark matter, would survive in its basic form. The Big Bang, the inflationary period, the formation of structure through dark matter and gravity, all of that would remain intact. But the precise values plugged into that model would shift, and several predictions that currently show tension with observations would need to be reassessed. Textbooks would be revised, not replaced, but updated with corrected parameter values and a new section on the importance of our local cosmic environment as a systematic effect in precision cosmology. And then there is the deeper question. If the cosmological principle is genuinely broken, if the universe has real large-scale inhomogeneities beyond what standard models predict, the theoretical framework itself would need extension. New terms in the equations describing cosmic evolution. New physics to explain why structure exists at scales larger than standard models say it should. That deeper revision is not guaranteed by void confirmation alone, but it would open the door more widely to theories that have been waiting on the margins of cosmology for exactly this kind of evidence. The largest structures in the observable universe should not be as large as they are. Standard cosmology sets a theoretical limit on how big a coherent structure can grow, given the age of the universe, the speed of gravity, and the initial conditions of the Big Bang. That limit sits at roughly 1 billion light-years. Structures larger than that should not exist as single coherent entities. They should fragment, dissolve into the background, fail to hold together. Several observed structures exceed that limit comfortably. The Sloan Great Wall, discovered in 2003 from the Sloan Digital Sky Survey, spans roughly 1.4 billion light-years. A flat sheet of galaxies and clusters connected into a single enormous structure. It sits roughly 1 billion light-years from us. When it was announced, it immediately became the largest known structure in the universe, a title it held for nearly a decade. Then something larger emerged. The Hercules Corona Borealis Great Wall was identified in 2013 and 2014, using gamma-ray burst positions as tracers of distant galaxies. Gamma-ray bursts are so luminous they can be detected across most of the observable universe, making them useful markers of galaxy positions, even at extreme distances, where ordinary galaxy surveys become sparse. The Hercules Corona Borealis Great Wall spans an estimated 10 billion light-years. It sits between 6 and 10 billion light-years away from us. If confirmed fully, it would be roughly 10 times larger than the theoretical limit for coherent structures, an order of magnitude beyond what the standard model says should be possible. The caveat is significant. The detection method using gamma-ray bursts is less precise than direct galaxy mapping, and the statistical case for the Hercules Corona Borealis structure as a single coherent entity rather than a chance alignment of independent clusters is still debated. More data is needed to confirm its full extent and internal connectivity. But even the Sloan Great Wall at 1.4 billion light-years presents a challenge, and surveys continue to find candidate structures at comparable scales in different regions of the sky. These enormous structures border enormous voids. The largest walls and filaments frame the largest empty bubbles. They are the walls of those bubbles, the concentrated shells of matter that formed as gravity evacuated the void interiors over billions of years. The bigger the void, the bigger the surrounding wall. If voids larger than standard cosmology easily accommodates exist in the real universe, then the walls surrounding them should also be larger than standard models comfortably predict. The two observations are connected. Anomalously large voids and anomalously large walls are two sides of the same structural excess. This excess is one of the strongest arguments that standard cosmological models, whatever their successes, are missing something at the very largest scales. Some ingredient, some physical process, some initial condition that produces more large-scale structure than the simplest version of the theory predicts. Candidates have been proposed. Primordial magnetic fields threading the early universe could have driven additional large-scale structure formation. Long-range modifications to gravity at cosmological scales could have seeded larger fluctuations than standard gravity predicts. Exotic inflationary models could have produced a different spectrum of initial density fluctuations than the simplest models assume. None of these has been confirmed. All of them are being tested as new surveys accumulate more data. And running underneath all of these structural puzzles is a single question that strikes at something deeper than any individual measurement. Here is a question that sounds philosophical, but has scientific teeth. If the universe has no edge, if space continues beyond the observable horizon in every direction without limit, then the structures we see inside the observable universe are just a sample, a finite region pulled from an infinite whole. And if the universe is truly infinite, it contains every possible configuration of matter and energy, including regions far emptier than the KBC void, and regions far denser than any supercluster we have mapped. Somewhere in an infinite universe, there exists a void so large it makes the Boet's void look like a bubble in a glass of water. The science of what lies beyond the observable horizon is necessarily indirect. We cannot see past it. Light from those regions has not had enough time to reach us in the age of the universe. The observable horizon sits roughly 46 billion light-years away in every direction, and everything beyond that is, in the strictest observational sense, inaccessible. But the physics of inflation, the theory describing the explosive expansion of space in the universe's first instant, makes predictions about what should exist beyond the horizon. Inflationary models generally predict that the universe is vastly larger than the observable region, potentially by an almost incomprehensible factor. Some models, predict a universe so large that our entire observable bubble would represent an infinitesimally small fraction of the whole. In a universe that large, the cosmological principle might hold perfectly across the whole, while still allowing our observable region to be a statistical outlier. We might live inside a void that is unusual relative to the cosmic average, while the average itself, computed across the full unobservable universe, remains homogeneous and isotropic, as the principle demands. This is an uncomfortable possibility for observational science. It would mean the anomalies we observe, the Hubble tension, the large-scale structures that exceed size limits, our possible void location, are all real but unreachable by any direct observation. We would be statistically unusual without any hope of confirming it by looking far enough outward. Some researchers find this possibility deeply unsatisfying. Science requires testable predictions. A theory that explains anomalies by placing their cause permanently beyond the observable horizon is difficult to distinguish from a theory that simply does not want to engage with the data. Others point out that the inflationary framework does make predictions within the observable universe, and many of those predictions have been confirmed. The inability to observe the full extent of the universe is a limitation of our position in space and time, not a flaw in the theory. What the void structure within the observable universe tells us is this: the universe, at least within the region we can examine, has more structure at large scales than the simplest models comfortably predict. Voids, walls, and filaments organize matter into patterns at scales approaching the limits of what theory says should exist. Whether that excess of structure reflects the true nature of all of reality, or whether it is a local statistical fluctuation that would smooth out if we could see farther, is a question that may never be fully answerable. But what we can do is keep measuring, and the next decade of measurements will push our understanding of void structure and large-scale organization to its absolute observational limits. There is a deeper problem hiding inside all of these discussions, and it has nothing to do with telescopes or data quality. It has to do with who is doing the measuring. The anthropic principle, in its simplest form, says that our observations of the universe are filtered by the fact that we exist. We can only measure the universe from locations where observers like us are possible. This sounds obvious, almost trivial, but its implications for cosmology are profound and uncomfortable. If life requires certain conditions, then observers will always find themselves in regions of the universe that meet those conditions, regardless of how rare those regions are. An observer asking why the universe has the properties it does will always find that those properties are compatible with their existence, because they could not have existed to ask the question otherwise. Apply this to cosmic voids. If void environments genuinely provide more stable conditions for the development of life, then an observer asking whether they live inside a void should expect the answer to be yes, more often than random selection would predict. The void is not a coincidence. It is a selection effect. This creates a scientific trap. If we find evidence that we live inside a supervoid, and if that evidence can be explained away as an anthropic selection effect, we have no way to distinguish between two very different situations. In the first, the KBC void is a genuine cosmological anomaly that requires new physics to explain. In the second, we live inside a void because that is where life could arise, and the void itself is unremarkable statistically across the full universe. Both situations could produce identical observational signatures. This is not a new problem in cosmology. Exactly the same tension arises with the cosmological constant, the value of dark energy. The measured value of dark energy is extraordinarily small compared to what quantum field theory predicts it should be. It is small enough to allow galaxies and stars to form, but not so small that it has no effect. If it were much larger, the universe would have expanded too fast for structure to form. If it were much smaller, gravity would have caused the universe to collapse. Anthropic reasoning says we live in a universe with this specific value because only universes with this value allow observers to exist. Whether that reasoning is satisfying or empty depends on what you believe about the multiverse and whether other values actually occur somewhere in reality. The void problem carries the same flavor. We may be in a void because voids are friendly to life. We may be in a void because it is a cosmological anomaly. We may be in a void by pure chance, and from inside the void, the data looks similar regardless of which explanation is correct. What breaks the degeneracy, if anything can, is statistics. If supervoids the size of the KBC void are genuinely too rare in standard cosmology to explain our presence there by chance, and if the anthropic explanation requires specific conditions that void environments meet better than other environments, then the three explanations make slightly different predictions about what the larger universe should look like. Future surveys probing the distribution of voids at large scales could potentially distinguish between them. But the possibility that our location has permanently biased every measurement we have ever made, and that we cannot fully correct for that bias because we cannot leave our location, is one of the most philosophically uncomfortable ideas in modern science. Stand on the wall of a cosmic void and the universe changes character completely. On one side of you, galaxies thin out into near nothingness. The void interior stretches away for hundreds of millions of light years, dotted with only the rarest, most isolated galaxy survivors. Space in that direction is cold in the most fundamental sense. Matter density is low, gravitational interactions are rare, and the evolution of structures has been slow and undisturbed. On the other side, matter thickens rapidly. The void wall is often a sheet of galaxies just 1 or 2 galaxies deep, a compressed concentration of matter that formed as the void evacuated and pushed material outward. Behind that sheet, filaments branch off in multiple directions, connecting to neighboring voids and to the denser nodes of the cosmic web, where galaxy clusters concentrate thousands of galaxies into a small volume. The wall itself is one of the most scientifically interesting environments in the universe. It is a region of rapid transition, where matter density jumps from nearly zero to something close to or exceeding the cosmic average over a distance of tens of millions of light years. Galaxies forming in this region of sharp density contrast experience an unusual combination of conditions. They sit close enough to the void interior to retain some of its quietness, receiving less gravitational disturbance from neighbors than cluster galaxies do. But they also sit in a filamentary environment where fresh gas can flow toward them along the cosmic web, feeding star formation. The result is a specific type of galaxy that researchers have identified as systematically different from both void galaxies and cluster galaxies. Wall galaxies, if we can call them that, tend to show moderate star formation rates, more regular morphologies than cluster galaxies, but less pristine than deep void galaxies, and chemical compositions that reflect a mixed evolutionary history. They are neither fully isolated nor fully social. They represent the gradient between the two extremes of the cosmic web. Studying wall galaxies helps scientists understand how environment transitions affect galaxy evolution, giving a more complete picture of how the cosmic web shapes the galaxies that inhabit it at every position along the density spectrum. But here is the feature of void walls that has the most significant cosmological implications. Void walls are moving. As voids expand, their walls propagate outward. Galaxies that were once in intermediate density environments find themselves swept up into the growing wall, compressed by the expanding void behind them. This ongoing compression creates a subtle but measurable signature in galaxy surveys. The packing density of galaxies along void walls is slightly higher than expected from simple collapse, because the wall has been accumulating matter from the expanding void for billions of years. This signal, called the void-galaxy cross-correlation, is one of the statistical tools researchers use to measure void growth rates and constrain dark energy. Every galaxy on the edge of a void carries information about the history of that void's expansion. By reading those galaxies carefully, by measuring their clustering, their velocities, their star formation histories, scientists can reconstruct the growth history of the void they border. That reconstruction is a time machine of sorts. It lets scientists measure what dark energy was doing not today, but billions of years ago, when the void was younger and smaller. And the history of dark energy's behavior over time is one of the most fundamental things we do not yet understand about the universe. There is a hard boundary in what science can tell us about cosmic structure. It is not a limit imposed by technology, or budget, or scientific creativity. It is a limit imposed by the universe itself. The observable universe is finite. Light travels at a fixed speed. The universe has a finite age. These three facts combine to create a spherical horizon around us, roughly 46 billion light years in every direction. beyond which no light has had time to reach us. Whatever exists beyond that horizon, and almost certainly something does, is permanently invisible to us from our current position in space and time. For most purposes in cosmology, this limitation is manageable. The observable universe is enormous, containing hundreds of billions of galaxies spread across tens of billions of light years. There is more than enough structure to study. But for the specific question of our position inside a potential supervoid, the finite observable volume creates a real problem. To confirm that we live inside the KBC void, scientists need to map the galaxy density in all directions around us out to several billion light years, and confirm that we sit within a region of systematic underdensity. That mapping is difficult but theoretically possible with the next generation of surveys. The void, if it exists at the scale proposed, fits well within the observable universe. The harder question is what lies beyond the void. To know whether our location inside a supervoid is statistically unusual or typical, we need to compare it against the broader distribution of voids across the universe. We need to know how often supervoids of this size appear, what surrounds them, whether they cluster, whether they sit inside still larger underdense regions. Answering that requires mapping the universe at scales approaching the observable limit. And at those scales, galaxy surveys become sparse. The number of galaxies visible in any given volume of sky decreases as distance increases, because only the most luminous galaxies remain detectable. The statistical precision of density measurements drops. Systematic errors from galaxy selection become harder to control. There is a specific distance at which our ability to map the cosmic web with sufficient precision to detect subtle underdensities effectively runs out. That distance sits somewhere around 5 to 8 billion light-years for current and near-future surveys. Beyond that, we can see individual bright galaxies and quasars, but not map density fluctuations with the resolution needed to trace void boundaries. This means the full context of our position in the universe, the structure of the cosmos beyond 5 billion light-years in every direction, will remain poorly mapped for the foreseeable future. We can confirm or refute the KBC void as a local structure. We cannot easily determine how unusual that structure is at the scale of the full observable universe. The implication is sobering. We may be able to confirm that we live inside a supervoid within the next decade. We may be able to measure the effect of that void on our cosmological measurements and correct for it. But whether that void is a rare anomaly or a typical feature of a universe with more large-scale structure than standard models predict may remain genuinely uncertain. The map we can draw has limits, and we are pressing against those limits in real time with the most powerful instruments our civilization has ever built. What we find at those limits may tell us everything, or it may raise questions that require capabilities we do not yet know how to build. Every level of structure we have found in the universe has revealed another level beneath it. Galaxies turned out to be part of clusters. Clusters turned out to be part of the cosmic web. Voids turned out to nest inside larger voids. At what scale does the hierarchy end? Standard cosmology has an answer. It predicts that above roughly 300 million light-years, the universe becomes truly homogeneous. Structure smooths out. Density fluctuations average to zero. The cosmic web dissolves into a statistical background indistinguishable from a perfectly uniform distribution of matter. But the observational evidence keeps pushing that homogeneity scale upward. Structures confirmed at 1 billion light-years. Candidate structures at several billion. The homogeneity scale has been revised repeatedly as surveys have extended to greater depths and found coherent structures where smooth background was expected. If the homogeneity scale is larger than standard cosmology predicts, the nesting of voids could extend to larger scales as well. The KBC void at 2 billion light-years might sit inside an even larger underdense region. That larger region might itself sit inside something bigger. Each layer of the hierarchy would be harder to detect, requiring a larger sample volume to distinguish from statistical noise. At some point, the hierarchy must end. Either the universe genuinely smooths out at some scale, or the hierarchy extends all the way to the observable horizon, in which case the cosmological principle fails completely, and the universe has coherent structure at every scale we can examine. The second possibility is radical. It is not currently the mainstream view. But it cannot yet be ruled out observationally, because we have not mapped the universe at sufficient precision at the largest accessible scales to confirm or refute it. Here is what makes this question so consequential. If structure extends to the observable horizon, then every cosmological measurement we have made is an average over an extremely non-representative sample. Our observable universe would be like a single pixel in an image too large to view. The pixel might be blue, but the image might be mostly red, and we would have no way of knowing. In that scenario, cosmology as currently practiced, deriving universal constants from local measurements, would face a fundamental epistemological problem. The constants we derive would be local constants, valid within our observable bubble, but not necessarily representative of the universe as a whole. We could not know whether dark energy has the same strength everywhere, whether the expansion rate is truly accelerating everywhere, or whether the physics we observe locally is universal physics. This is the deepest and most unsettling version of the void question. It does not just ask whether we live inside a local underdensity. It asks whether there is such a thing as a universal physics that can be derived from one location. Science has always assumed the answer is yes, that the laws of physics are the same everywhere, that constants measured here apply everywhere, that our local sample of the universe, despite its evident complexity and structure, is representative enough to support universal conclusions. The void structure we observe is not yet enough to overturn that assumption, but it is enough to make it a question rather than an axiom. And that transformation from assumption to question is how science always moves forward. Consider a civilization that evolved inside a deep cosmic void, one with a galaxy like ours but sitting in a region twice as underdense as the KBC void. Their astronomers look out at the sky and try to make sense of the universe. They measure the expansion rate, they count galaxies, they map large-scale structure, they build a cosmological model. What would they find? Their local expansion rate would be inflated even more than ours, because their underdense environment exerts even less gravitational resistance to expansion. They would measure a Hubble constant significantly higher than the true cosmic average. When they tried to reconcile that with measurements from the cosmic microwave background, their Hubble tension would be larger than ours, and potentially large enough to seem irreconcilable with any simple extension of the standard model. They would count galaxies in their local volume and find fewer than expected. Their estimates of the average matter density in the universe would be biased low. Their constraints on dark energy would be systematically skewed toward a higher dark energy density than actually exists, because their inflated local expansion rate would look like stronger dark energy in their models. They would see large-scale structure anomalies. Their sky would show fewer galaxies in the direction of the deepest void interior and more in the direction of the nearest filament. Their dipole anomaly would be larger than ours. Their cosmic microwave background might show a cold region corresponding to the deep interior of their even emptier void. Their cosmological model would be wrong in consistent ways, all pointing in the same direction, all biased by their location, but none of the individual biases would be large enough to immediately expose the systematic error. They might eventually figure it out, the same way we are attempting to do now, by noticing that multiple independent measurements disagree with each other in consistent ways, by building increasingly detailed maps of their local structure and finding the underdensity that surrounds them, by developing theories about how void environments bias cosmological measurements and applying those corrections. Or they might not figure it out within their civilization's scientific lifetime. The corrections required are subtle. The evidence for them is indirect. The alternative explanation, that the standard model simply needs new physics at large scales, is intellectually compelling and might consume generations of theoretical effort before the local environmental explanation won out. This thought experiment is not purely hypothetical for us. We are those observers. We are making those measurements, seeing those tensions, debating those explanations right now. The possibility that we are in exactly the situation of the hypothetical void civilization should be taken seriously because the observational signatures are consistent with it. The difference between us and that imagined civilization is that we have already begun to suspect our location might be unusual. The KBC void hypothesis exists. The Hubble tension is recognized as a systematic problem that might have a local environmental explanation. The tools to test that explanation are being built. We may be the first generation of cosmologists with both the suspicion and the capability to actually check whether our cosmic address is biasing our view of reality. Whether we succeed in answering that question, and whether we succeed in time for the answer to reshape our understanding before we build an entire generation of experiments on potentially biased foundations, is a genuinely open question. Suppose the KBC void is confirmed. Suppose its depth and extent are measured precisely enough that scientists can calculate exactly how much our local expansion rate is inflated above the true cosmic average. Would we then be able to correct our measurements and recover the true cosmological parameters? In principle, yes. The physics of how a void environment affects expansion rate measurements is well understood. Given a precise characterization of the void's density profile, its size, its shape, and how it connects to surrounding large-scale structure, scientists could in principle calculate a correction factor and apply it to every local cosmological measurement that depends on the expansion rate. That correction would pull the locally measured Hubble constant downward toward the value inferred from the cosmic microwave background. The Hubble tension would dissolve. The age of the universe would be revised slightly upward. Dark energy constraints would shift. A self-consistent picture of the cosmos would emerge, one that accounts for our unusual vantage point. This is achievable science. The challenge is that the correction requires knowing the void's properties with a precision that current surveys do not yet provide. The depth of the underdensity matters enormously. A void that is 15% underdense produces a different correction than one that is 25% underdense. The uncertainty in that number translates directly into uncertainty in the corrected cosmological parameters. Getting the void characterization right requires mapping galaxy density with high precision across a volume spanning several billion light-years. That is exactly what the Rubin Observatory and Euclid are designed to do. Within the next decade, the measurements needed to compute a meaningful void correction should be available. But applying the correction also requires understanding the void's geometry in detail. Is it roughly spherical? Is it elongated in some direction? Does it have internal density variations, smaller subvoids and relative overdensities within the larger underdense region? Each of these geometric details affects how the expansion rate bias plays out in different directions across the sky, and a geometrically complex void would require a direction-dependent correction rather than a simple uniform one. Direction-dependent corrections in cosmological data analysis are technically challenging. They require careful treatment to avoid introducing new systematic errors in the process of removing old ones. The correction itself would need to be validated against independent data before being trusted as a definitive fix. And there remains a more fundamental question underneath the technical challenges. If the cosmological principle is breaking down at large scales, not just because of the KBC void, but because of a genuine failure of homogeneity at scales beyond anything we have mapped, then no single correction derived from our local environment would be sufficient. The universe would need to be described by a more complex model, one that allows for position-dependent cosmological parameters and abandons the mathematical simplicity that has made the standard model so powerful. That would be a genuine revolution in cosmology, a harder and slower process than applying a single correction factor, but also a more complete and honest reckoning with the universe as it actually is, rather than as we assumed it to be. The tools are almost ready. The data is starting to arrive, and the final answer to where we stand in the cosmos and what that means for everything we think we know is closer than it has ever been. Pull back to the widest view available to human knowledge, the observable universe, 46 billion light-years in every direction. Inside it, hundreds of billions of galaxies, organized into clusters and superclusters and filaments and walls. Between those structures, the vast dark bubbles of the cosmic web, the voids that make up the majority of space by volume. Somewhere inside one of those bubbles, on the outskirts of a supercluster that drains toward a gravitational low point 250 million light-years away, in an average spiral galaxy on the edge of a local group of several dozen galaxies, orbiting an unremarkable star among 400 billion others, sits every telescope we have ever built, every measurement we have ever taken, every conclusion we have ever drawn about the shape and fate of reality. We have been measuring the universe from inside it, from a specific location within it, from a location that may be systematically unusual in ways we are only now beginning to quantify. This is the situation we find ourselves in. And it is, depending on how you look at it, either deeply humbling or deeply exciting. The humbling version says we may have been wrong about the most fundamental numbers in cosmology for decades, not because of careless science, but because our position in the universe introduced a quiet, consistent bias into our measurements that we had no way to detect until our surveys became large enough to see the structure surrounding us. The exciting version says we are the first generation of humans with the ability to recognize that bias, to map the void we inhabit, to correct for it, and to build a more accurate picture of the cosmos than any previous generation could have achieved. Both versions are true simultaneously. The history of astronomy is the history of displaced perspectives. We thought Earth was the center of the solar system, then discovered it was not. We thought our star was the center of the galaxy, then discovered it was not. We thought our galaxy was the center of the universe, then discovered there was no center. We assumed our position in the cosmic web was typical, and now we are discovering it may not be. Each displacement was disorienting in the moment and clarifying in retrospect. Each one gave us a more accurate, more honest understanding of where we actually stand. If we confirm that we live inside a supervoid, it will be the next displacement. Our cosmological map will need revision. Our fundamental parameters will shift. Our model of the universe will become more complex and more accurate simultaneously. And then, from our corrected position, we will look outward again. We will build new telescopes, run new surveys, push our observable horizon as far as physics allows. We will find new anomalies at the next scale of structure, new tensions between measurements, new mysteries in the ancient light. Because that is what the universe keeps doing. Every time we extend our reach, it reveals another layer of complexity we did not anticipate. Every answer opens 3 new questions. Every cleared horizon shows a stranger one behind it. We are not at the end of this story. We are somewhere in the middle, holding instruments that are almost good enough to see the next surprise, living inside a cosmic hole whose depth we are just beginning to measure, looking up at a universe that is larger, stranger, and more structured than any model we have yet built to contain it. The void surrounds us, the questions multiply, and the next measurement is already being taken.